Newton's rings experiment. This is the experimental setup for Newton rings experiments. Here AB is the plain glass plate and P is the plano convex lens, and S is the sodium lamp. This is the source for light in this experiment, and another glass plate is placed here, which is the angle 45 degrees with the sodium lamp, and this is the microscope. Through microscope we can observe the Newton's rings in these experiments. Here a light source incident on the plain glass plate with 45 degrees angle and get reflected another 45 degrees angle. Then we can observe the Newton's rings through the microscope. Here a thin film is formed between the plano convex lens and a plain glass plate AB. Here interference is due to the reflected light. Again two cases. Case 1, condition for the bright light and condition for the dark rings is the another condition. Here condition for the bright ring is the 2 mu t cos theta is equal to 2n minus 1 into lambda by 2, where n is equal to 1 to 3, etc. Here if theta is very small, then cos theta will be 1, and here we did the experiment in the air, so air film refractive index is equal to 1. Then we can write this equation, 2t is equal to 2n minus 1 by lambda, and here in this equation 2t is equal to n lambda. From this figure we can write like this: EP into HE is equal to OE into 2R minus OE. Here EP is equal to R and also it is equal to EH, and OA is equal to PQ and PQ is also equal to 2T. Then EO also equal to T. Then you can substitute these values in the here. EP is equal to HE, that is equal to R, and OE is equal to PQ, that is equal to T, and 2R minus T is approximately equal to 2R because T very small compared to R value. Therefore, if you substitute these values here, R square is equal to 2RT. Then we will get the T value. T is equal to R square by 2R. Then you can substitute this T value in equation 1. Here 2 into R square by 2R. Then 2 cancel. R square is equal to 2n minus 1 R lambda by 2. That is equal to R is equal to square root of 2n minus 1 R lambda by 2. For dark fringes, R square is equal to n lambda R and R is equal to square root of n lambda R. When n is equal to 0, the radius of the dark ring is 0. Here if you substitute the 0 value, then you will get the 0 radius of the dark ring, and radius of the bright ring is, if n is equal to 0, then R lambda square root of R lambda by 2. Therefore, the center is dark. Alternatively, dark and bright rings are produced in this experiment. The radius of the dark ring is proportional to square root of n, square root of lambda, square root of R. In case of radius of the bright rings is proportional to square root of 2n minus 1 by 2, square root of lambda and square root of R. Determination of wavelength of light source using Newton's rings. If D is the diameter of the dark ring, then D is equal to 2R. R is the radius of the dark ring. Then diameter of the dark ring D is equal to 2R. Then that is equal to 2 into square root of n lambda R. For the dark center ring, that is n is equal to 0, then the diameter of the dark ring D is equal to 2 square root of n lambda R, that is equal to 0 because n is equal to 0. This corresponding to the center of the Newton's rings. While counting the order of the dark ring 1, 2, 3, etc., the central ring is not counted. Therefore, the first dark ring n is equal to 1 and the diameter d1 is equal to 2 square root of lambda r. For the second dark ring, n is equal to 2, then d2 is equal to 2 square root of 2r. You can substitute n values in this here. And the nth dark ring will be dn is equal to 2 square root of n lambda r. Neutron rings are viewed through the beaming here microscope through the glass plate which are angled with 40 degrees towards the sodium lamp. Neutron rings are viewed through the B by the traveling microscope M focused on the A film. Circular bright and dark rings are seen with the center dark with the help of a traveling microscope. Measure the diameter of the nth dark ring, that is equal to dn is equal to 2 square root of n lambda r. Then dn square will be 4n lambda r. Measure the diameter of the m plus nth dark ring. Then you can write above equation like this: dm plus n is equal to 2 square root of, you can replace the m plus n in m plus n square into lambda r. That will be d square m plus n is equal to 4 into m plus n lambda r. This is equation 2. If you subtracting equation 1 from the equation 2, then we will get d square m plus 1 minus dn square is equal to 4 into m plus 1 lambda r minus 4 n lambda r. Then 4 n lambda r, 4 n lambda r and 4 n lambda r will be cancelled. Then we will get the 4m plus 4m lambda r. That is equal to d square m plus n minus dn square is equal to 4m lambda r. Here we can get the wavelength of the source lambda is equal to d square m plus 1 minus d square n by 4m r. R is equal to curvature of the planar convex lens, d square m plus n minus dn square by 4m lambda. By using these two equations, we can get the wavelength of the light source or curvature of the planar convex lens. This is the pattern for Newton's rings. We can get the center dark and bright and dark alternative fringes. And another one is the determination of refractive index of the liquid. To find the refractive index of the liquid, we have to do the two experiments. First one is the, as I said previous slide, we have to find the dn square plus here d square m plus 1 minus d square is equal to 4m lambda. We have to do that experiments in A. And next experiment, we have to place this plain glass plate and planar convex lens in a liquid, which we have to find the refractive index of this liquid. In this system, again the diameter of the same mth and nth dark rings are to be obtained. Then we have d dash square n minus d dash square m is equal to 4m minus n lambda r by mu. Mu is equal to refractive index of the liquid. Then finally mu is equal to dn square minus d square n minus dm square by d dash square n minus dm square. From this equation we will get the refractive index of the liquid. For this we have to do two experiments. One is at air. Air means this planar convex lens and plain glass plate should be in air. And next experiment, we have to place this arrangement in a liquid. That liquid which we have to we are going to find the refractive index. Then we have to measure the dn square, d square n minus dm square is equal to 4m minus 1 into lambda r by mu. Here mu is the refractive index of the liquid. Then mu is equal to, for example, here this is the equation, d m plus n square minus dn square is equal to 4m lambda r. then you can take the ratio, then this 4m minus 1 into lambda r will be cancelled, then we will get the mu is equal to dn square minus dm square by d dash square minus d dash square m. From this equation we will get the refractive index of the liquid. Here are the application of interference. By using the interference method, we determine the wavelength of the liquid source, as I explained previously, under determination of radius of curvature of the lens and the refractive index of the transparent liquid, testing of optical flatness of a lens and other used as components of optical instruments, finding the thickness of thin transparent glass plates, and determination of diameter of the thin wire, which is also called wedge method, and the data read and writing of CD or DVD, construction of hologram in holography. These are the few applications of interference.